Hello, so we are going to go over together real quick the notes on the physics of sound and the Doppler effect. So this is attached to your day here, the absent work for Thursday and Friday. So you should have a handout that looks like this. I'm just going to go through the notes today and explain them. I know everything's already filled out, but we do have a formula on the back that's particularly difficult at first, so I figured a quick explanation will help. There's some practice problems that are also attached to this assignment. I did supply the key for the practice problems so that you can check your understanding when you're done for those of you that are absent or quarantined for the day. This formula, it is going to be on both the upcoming tests that we'll be having, which our first test for the quarter is going to be next Thursday and Friday, April 29th or 30th, depending on your block day. This formula, the Doppler effect formula, will be on there. So making sure you're checking your understanding and you understand it is important. And then it's also going to be on our fourth quarter exam. So please don't just copy off the worksheet. Key, again, it's there for you to check your work to make sure you're on the right track, or if you need to take time to ask questions and to get some reteaching from me. So our notes today are on sound. So what is sound? What makes sound? What are some properties of sound that can change? And then a phenomenon known as the Doppler effect. And I am going to provide too a YouTube clip for you to watch as well that'll give you a better visual of what the Doppler effect exactly is. So sound, by definition, is pressure variations that are caused by vibrations that are transmitted through matter. So anytime something vibrates and it causes a change in pressure and that vibration travels through matter, it is able to create sound. Now, sound in particular is classified as a longitudinal or also a compression wave, interchangeable terms, based on how sound travels. So as something vibrates, in particular, in this picture here, we have a speaker. As something vibrates, it's going to move matter around it. So in this case, air. Now, when it vibrates, it's going to cause a collision with those air particles that are around, in this case, the speaker or whatever the source of vibration is. So that's going to cause some collisions at the atomic level. We'll have some air particles that are going to quickly compact with each other for a split second, and then they're going to bounce off of each other. And then they're going to collide again with another group of matter, in this case, the air, with a collision. And after the collision, bounce off. And so it's just a repetition of pushes, pulls, or compactions and pushes until it reaches our ears. And then we perceive these vibrations as a particular sound. So sound moves as a compression wave, where matter is getting compressed and expanded over and over again as it travels through a particular medium. So pretty much all material can vibrate or can go into what is called resonance, which is what allows different materials to make sound and to make sound that has different pitches to our ears. And this is when something is forced into a particular frequency and that, forced into a vibration, and that vibration matches the natural frequency at which that object can move or vibrate. So pretty much any source of matter can vibrate. However, it does take a particular frequency in order to set it into vibration. So a very light smack on the table here isn't going to cause a high enough frequency or set this into resonance in order for you to be able to hear it. But if I really smack it, then that force will produce a higher frequency of vibration, and that allows it to vibrate enough then to create sound. Now we have some terms that are related to sound waves from our waves unit that alters how you hear or perceive sound. The term pitch refers to the frequency of the vibration. So remember, wave frequency is the number of oscillations that occur in a second's worth of time. Traditionally, we've been working with transverse waves. So frequency would be the number of crests and troughs that you have within a second's worth of time. So with longitudinal waves, it's the numbers of compression and expansions you have within a second worth of time. So a higher frequency wave means you have more compressions and expansions happening, so a more violent collision that's occurring at the atomic level than you would with a lower frequency wave. And we kind of have just a general rule: the higher the frequency, the higher the perceived pitch is going to be. And so in music, it's the different frequencies that you can set your instrument to vibrate that produces the different notes. So lower vibrations have those deeper notes, and then really high vibrations have those really high frequencies and higher pitches. Loudness. So how loud a wave is going to be differences in the pressure variations, so the size of the amplitude of the sound. So the higher the displacement, the greater the difference in the pressure variations, the louder the sound is going to appear to us when we hear it. So how amplitude is visualized within a sound wave is tighter areas of compaction. So something that's louder is going to be more violent. So it's going to have tighter areas of compaction of matter than one that is not as loud, that has less energy and it's a little bit weaker to it. Now, typically loudness is measured in decibels. It's logarithmic, so it goes by scales of 10. A 10 decibel sound wave is going to be around at a soft whisper, whereas once we get to 110, it becomes painful to your ears. So around what you would hear at a loud, like a loud rock concert. So just to kind of compare and contrast, just to summarize this sound portion of the notes. So amplitude, so the displacement of the wave from rest. Again, our transverse waves, it's the height of the wave. Amplitude determines how loud it's going to be. So a quieter sound, not as displaced. A louder sound, a greater displacement. Again, it's a longitudinal wave though, so it's going to be tighter compactions that is actually happening when it comes to a sound wave. And then frequency, so the more oscillations that occur within a second's worth of time, it's going to have a higher pitch, so it's going to have that more annoying sound to it that's going to hurt your ears, versus a lower frequency where it'll be a lot lower and deeper once you hear it. So the second half of our notes, where our formula is going to pop up, is the Doppler effect. Now, the Doppler effect is a phenomenon that we experience every day, but it's really only noticeable when things are moving fairly fast and sounds are very loud. Now, what the Doppler effect is the apparent change in pitch. So the change in pitch the change in the actual pitch of the sound doesn't really happen. It's the apparent change. So it seems like the pitch changes simply because an object moves. And so remember, pitch depends on the frequency of a sound wave. So I'm sure at some point in your life, you were in a car or you were outside and you had an ambulance heading towards you and moving past you, or a train heading towards and moving past you, or something with a siren, a very loud noise that approached you and then went past you. So the Doppler effect can be easily heard as that really high and then drop, so the meow that you would hear if you heard something racing or moving quickly by you. So it's the pitch that appears to change simply because something's moving, but when in actuality, the pitch isn't changing at all. So what happens when something emits sound? When an object is stationary, so it's not moving, a sound wave is going to move evenly in all directions. So the frequency remains constant, and since the frequency remains constant, the pitch doesn't change. So it has a particular pitch that it's going to maintain as the sound is being emitted. Now, if that object is moving, or if you are moving, that pitch is going to change. So as something approaches you, or as you approach a sound source, the direction in which the object is moving, or the direction in which you are moving, those sound waves are going to become compressed. They're going to become condensed. And so the direction in which the sound source moves compresses those sound waves, and a higher frequency means we have a higher pitch, and so it's going to sound louder in the direction that the object is moving. On the opposite side of things, so on the side in the direction in which the sound source is not moving, the wavelengths are lengthened, thus increasing the frequency, and so it sounds lower pitched to you. If you watch the example videos that we have, you'll be able to hear a siren, something with a siren approaching towards somebody standing still and then moving away. And so you should be able to hear within that clip that the siren sounds louder as it moves towards you, but then sounds deeper and lower once it moves past. Now, the pitch of the siren never changes. It just appears to be higher pitched to you based on your position and how the object is moving, or appears to be lower pitched to you, again, based on your position or how the object is moving. So higher pitches are perceived when either you're moving towards the sound source or the sound source is moving to you. So that condenses the wavelengths and thus increases the frequencies. And a lower pitch is heard when either you move away from the sound source or the sound source moves away from you. So that lengthens the wavelengths and produces a lower frequency that is observed. So that'd be a good time to, if you don't have a calculator handy, grab one, just so we can practice entering in our practice problems together, just to make sure we're doing them correctly and putting everything in our calculator correctly before we try out some of the problems on the attached sheet. So our Doppler effect formula looks a little wild and crazy here. These formulas are very detailed specific. So you do have to very closely read a story problem because you're going to have to not just pull out numbers, but you're going to have to pull out context clues as well in order to answer these questions correctly. So it does take for careful reading of story problems, which makes them a little tough in the beginning here. Now, what the Doppler effect formula says is that I can find the Doppler frequency. So this is the perceived frequency, so the higher or lower pitch that I think I hear, by taking the actual frequency of the sound source, so what the frequency is that's actually being emitted from the sound source, and then I can multiply that by V, which stands for the speed of sound. It is a constant. So again, our constants, those never change. So we're always going to use 343 meters per second to represent the speed of sound. So this is the speed in which sound travels through air. So the speed of sound plus the speed of the detector. So the detector is the person, or it could be an object, something the sound wave bounces off of, that hears or that perceives the sound. Now these pluses and minuses stay fixed, but the numbers of the velocities can be positive or negative based on how the individual is moving. So it's positive if the individual is moving towards the sound source, or it becomes a negative if the individual moves away from the sound source. So let's say I had somebody that was walking 1 meter per second and they hear a siren from a car. So at the top here, this would be 343 plus, and then depending on what the detector is doing, it would be a positive or negative 1. So if the detector is heading towards the siren, it'd be plus 1 meters per second. If the detector was walking away from the siren, then it would be 343 plus a negative 1 meters per second. Now you could technically change that then to a minus, but that does then alter. The big confusion that happens with that, though, in previous years is that we then think that this starts off as a minus. So I always tell everybody, these never change. You're just going to leave these numbers positive or add a negative if needed, but never change these numbers. Otherwise, traditionally, we write the formula wrong, and then we get the answer incorrect because of that. Okay, went on a little rant here. And then, so VS, so that stands for the velocity of the source. So again, in this case, this would be my siren, if we got the siren and the person walking 1 meters per second. So this is how fast does the sound source move, because the sound source could also be moving. And same thing, it's positive or negative based on how it's moving. So positive if it is moving towards the detector, or negative if it's moving away. So let's say my person is stationary, not moving. They have a velocity of 0. So this would just be 343 plus 0. My detector, my sound source has a velocity, let's say it's a car, so maybe it's going like 20 meters per second. If it's moving towards the person, it'd be 343 minus 20 meters per second. And if it's moving away from the person, it'd be 343 minus a negative 20 meters per second. All right, so here's a couple examples of what these problems look like. So again, I know this is filled out for you already, but this would be a good chance to maybe get a piece of paper and kind of work it out on your own, just so you get that practice. And then to have a calculator and try this out in your calculator. So again, just to check to make sure you're getting the same numbers that I am. All right, so you have a person that sits on a bench and a train comes towards the person at a speed of 31 meters per second, blowing a 305 hertz horn. And I want to know what frequency horn is heard by the person. So the frequency that the person hears is the Doppler frequency. And if I'm looking at my formula here, I need to have a frequency of the sound source. So what frequency does the sound source actually have? So in this case, it's a 305 hertz horn. So 305 hertz for FS. The two V's here, they're constants. So V is always 343 meters per second. And now where the detail comes in is for the detector and the sound source. So how fast are they moving and how are they moving? So the detector is whoever hears the sound. So I have two things in this story problem. I have a person on a bench and a train. So the train has the horn. So the train does not hear the sound. The train is what's making the sound. So my person sitting on the bench that I'm trying to see what frequency they hear it, they are my detector. So they're the one that detects, that hears the sound. So to figure out how fast the person's going, I'm going to read the story. If I don't see anything that says meters per second next to that individual, then I'm looking for a context clue to see if they're at rest. So here the person is sitting on the bench. So if you're sitting, you're not moving. You have no velocity to your motion. So the detector here is just 0 meters per second. The source of the sound, so that's how fast does the sound source move. So in this case, it's the train blowing the horn. So they're my sound source. And they are moving. They have a speed of 31 meters per second. And they are moving towards the person. So towards is a positive direction. So I'm going to leave that as a positive number. I'm going to leave that as a positive 31 meters per second. So when I go to put this in my calculator, I'm going to start off with the frequency of the sound source, so 305 hertz. And then I'm going to add up together, and if you use parentheses, that's fine, or you can add it yourself to make it a number, that's fine too, but I'm going to add together the speed of sound plus the speed of the detector. So 343 plus 0 meters per second, since they're not moving, I can just leave it as a positive 0. It doesn't matter if I made it positive or negative. Anything plus 0 is just going to be 0, right? So 343 plus 0 just leaves me with 343 on top. And then I'm going to divide it by 343 minus the positive 31 meters per second. So just 343 minus 31. Again, when you go to divide, you either need to use parentheses around here if you're not going to subtract it yourself, or you can subtract it yourself and make it a single number. But if you don't put parentheses around here and you type it in like this, then your calculator is going to do order of operations wrong. It's going to multiply this first and then just divide it by 343 before subtracting, which you don't want to do that. You want to divide it by this minus this. So either use parentheses or subtract it yourself. So 305 times 343 on top over 312, and you should be getting 335 hertz. Now, the nice thing about these problems is we can check ourselves to see, does our answer make sense? So if the train's coming towards the person, those sound waves should be getting compressed. So the frequency should be increasing as the wavelength is lowered. And so the perceived Doppler frequency then should be a higher frequency wave than the original sound source. So in this case, 335 is a little bit higher here than 305. So that means that we probably solved this problem correctly, since the perceived frequency is higher than the original source, as it should be. All right, so now let's say I still have this person on the bench. Now the train is continuing to move, and now the train goes past the person on the bench. And so now I want to see what frequency does this person perceive now as the train moves away from them. So the train still has the same original frequency for the horn, 305 hertz. Again, this is the actual frequency of the sound source. The Doppler frequency is the apparent, kind of the fake frequency that's perceived. Speed of sound doesn't change since it's a constant, so it's 343 meters per second. The person is still sitting on the bench. The person is the one that is sitting on the bench is the one that is still hearing the horn, so they are still the detector. So their velocity is 0 meters per second. Now, the train is maintaining the same speed, 31 meters per second, but now the train moves away from the detector. So since the train is moving away, that 31 meters per second is now a negative. So there's my context clue of whether to make it positive or negative. So I'm going to treat this as a negative 31 meters per second. So when I go to plug my numbers in, 305 times 343 plus 0 over 343 minus a negative 31. So now I'm going to use this as a negative number. Should be getting 279.7, or we can just round that up to 280 hertz. And again, I can check to see if my answer makes sense. Because if the train is moving away, then the perceived frequency should be lower. The wavelengths are getting lengthened. The frequency as a result then will decrease. So it should sound like a lower pitch to the detector. So 280 is less than 305. So again, I can assume that I have answered these questions correctly. Now, I know I went through these notes fairly quickly, a little bit quicker than I would have done in class. Maybe that's a blessing or a curse. I guess I don't really know. I'll let you decide. But feel free to reach out to me if you still have any questions. The assignment is attached to as a material here. So a few Doppler effect problems for you to try on your own. And then again, the key is also attached as well. So please use that to check your understanding, to check your answers, to make sure you're on the right track with these problems. And then I will be available during our enhanced virtual Wednesday times if you still have any questions about the Doppler effect and you wanted to have a face-to-face meeting. So that schedule is posted in Google Classroom. So feel free to look that over and send me an email and we can schedule an appropriate time for you. Hope you are all doing well and have a good day.